Hello, 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 hello. Testing, testing. Hello, 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 hello. Good. Okay. Um. God, where did I leave off? I'm not sure. I think this exercise is something I was working on my notepad, so bear with me. Now maybe I can remind myself of what I was actually doing. So I just need to share this link. How do I find my name? Here it is. Yes. Share. Copy. All right. Okie dokie. Let me just make sure I've got myself back on. Yes, I do. Okay. Yeah, so I was doing stuff over the weekend and haven't looked at it since. But I think I was dealing with uh, the thing I did wrong the last time, right? So we went through all these equations and then I realized that I'd completely mucked up. And the fact of the matter was I just took, first of all I took the wrong equation. I muddled it up, and second of all, I did a very roughly the same thing as well. I'll just show the book for reference sake. Um, but anyway, I started to put complex numbers in. I started to understand the magnitude a bit more. The fact that the magnitude is always a square root of the inner products. Um, also tried to redraw the original diagram that it mentions here. Let's see. I think it says. Uh, Let me see. I think it says here somewhere. What if you had started with linear dependent base and at some point, no, it wasn't that one. Wow, where was that? Yeah, here it is. Let us take two non-parallel vectors on a plane, right? So this part here, I started to draw it out. I tried to realize what it was talking about. I think I got to a point where I was like, okay, I see this. So then I moved on to this little thing, exercise 1.3.1. So I think I didn't go all the way, but I made some effort in trying to do it, and so I think we'll restart and try and recap over that. So that's what we shall do today. Yeah, okay, right. I don't think you could even see that because clearly the camera's too small, but I've done stuff, right? Good. So let me just test this tablet's working. Yes, it is. Great. Um, let's go back through this a little bit. So it says that the vector 1, the basis, is equal to um, the entire vector, not the component or the basis, divided by the length of that, where this is the square root of the inner product of them. And then it says, let's just take the following. Clearly, if that's the case, then the inner product squared is going to be equal to 1, of course, because the square root of the square root of this squared is uh, the. Let me just think about this. So the inner product divided by the inner product to the square root and then squared again is of course going to be 1. And I think I totally missed how obvious that was, though, I went through it and we figured out, proof by the pudding. And then it says, as for the second vector in the basis, consider this. It says there's a second one in the basis, uh, and it's equal to the second vector minus the first basis, and then the inner product of the two, which is 2 minus the part pointing along the first unit vector. So the unit vector is this inner product, I guess, of these. No, yeah, because it equals 1. So that becomes the unit. No, that's the. Is that the unit vector? No, that's the identity. So which is 2 minus the part pointing along the first unit vector. So why is that? Because here's our basis multiplied by or scaled by the inner product. The inner product returns a single number, so it's going to be a little bit more of that 1, and so it's whatever that is minus a part of this number 1, right? So if you have, I love how I'm trying to explain this even though I don't really know it, but it's saying that, let's imagine there is, what am I doing? Sorry, wrong thing. Let's imagine there's this vector, and it's equal to, and it's minus the original basis, which is this one up here. Well, if we're going to minus that basis multiplied by some inner product, well, the inner product equals a number, let's call that a. And so if we're just scaling this, and then we're taking it away from the one that we're talking about here. So which is 2 minus the part pointing along the first unit vector. Think of the arrow example as you read on. Not surprisingly, it is orthogonal to the latter. So it's saying that this vector 2 is orthogonal to this one. Not surprisingly, it says. So the inner product of the basis of the first and the second is equal to the inner product of this minus the inner product of 1 scaled by this. So if 1, 1 is a scalar and it's multiplying this by some certain number, so okay, so let me just put this. If you had 1, 1, it's saying that 1, 1 equals 1, right? And so here we're taking whatever 1, 2 is, which is some number. Let's call this 5. Well, actually, let's just call it 2. And then we're scaling it by 1. So 1 times 1 equals 2. And so therefore this 1, the inner product of 1 II minus this, well, or minus that is going to be the same, right? So that does make sense. Of course it equals 0 because you're minusing it. Good. So this is making sense so far. And it says we now divide by that. No, we now divide 2 by its norm to get 2, which will be orthogonal to the first and normalized to unity. So we now divide 2 by its norm, or more so this, I guess. To get 2. So why is that? Because a vector would have, let's say, coordinates, and with dividing by the length of so I think um I've lost the point of the prime actually. So 2 prime, what is 2 prime in this case? No, it's good that Windows works. Wonderful. It always works so well. When closing a window is not enough to actually close the window. Great. Um, I don't quite get this yet. Not surprising it was orthogonal to the latter, yep. But then we now divide 2 by its norm to get 2. So let's go and ask GPT-4 about this. So it says the page then says let's no, we now divide 2 by its norm to get 2, which will be orthogonal to the first and normalized to unity. What does this mean? Let's see what it says, because I actually have lost this a little bit. Oh, it's so hot today. Nice. This passage is describing the process of constructing an orthonormal basis. Here's a breakdown of the sentence. We now divide 2 by its norm. This means that you're normalizing the vector 2. Normalizing a vector means making its length or magnitude equal to 1, but keeping its direction unchanged. To do this, you take every component of the vector and divide it by the vector's norm or magnitude. This produces a unit vector. So let's try and understand what that's just said. If we're dividing it by its norm, here we go. To get 2, the result of this normalization process is a new vector labeled 2. This vector is in the same direction as 2 prime, but its length is 1, which will be orthogonal to the first by the construction process described earlier, i.e. 2 equals 2 minus 1, the vector 2, and thus 2, since normalization doesn't change the direction, is guaranteed to be orthogonal or perpendicular to the first basis vector 1. In simpler terms, their inner product is 0. And normalized to unity, this is another way of saying that the magnitude or length of 2 is 1. Normalized to unity means the same as saying made to have length of 1. In essence, this process is part of the Gram-Schmidt procedure for orthonormalization. The end goal is to create a set of basis vectors that are both orthogonal to each other, perpendicular, and have a length of 1 normalized. This set of vectors is particularly useful in quantum mechanics and many other areas of linear algebra because calculations with such vectors are often more straightforward. I didn't understand this, so let me try recap this. Could you write this again? A few of the bits you've tried to type went wrong. Let's just see what it does again. Okay. We now divide 2 by its norm. This step involves normalizing the vector. To normalize a vector means to adjust its length or magnitude to be equal to 1, while preserving its direction. This is achieved by dividing each component of the vector by the vector's overall magnitude. So let's say 2 prime is equal to 0, 1. Now the magnitude of 2 is going to be equal to oh gosh, I've forgotten how to do this. 2 by dividing each component of the vector by the vector's overall magnitude. So how did we get the magnitude of these things? Let me just check my book here. The magnitude is, oh yeah, the square root of the inner product. It's the square root of the inner product. So this is the square root of the inner product. Which would equal a full number. So let's imagine what this will be. It'll be 0 times 0, 0 times 0, and then 1 times 1, and so it's going to equal 0, 1, and then, oh no, sorry, yeah, idiot me, it's, we're not taking the, what am I doing here? So, this will actually be 0 times 0 plus 0 times 1 plus 1 times 0 plus 1 times 1, which is 0 plus 0 times 1 plus 0 plus 1 times 0 plus 1, which equals 1. So the magnitude, the inner product is 1. So the square root of 1, I don't actually know what it is. Guess it's 0 or something. Square root, where are you? Square root, where are you? Square root of 1 equals 1, okay. And so this equals that divided by this, which equals 1. Then you go 0, is it 0 divided by 1? It says, yeah, so then the norm what's the symbol for the norm of um, 2 prime? I thought that was the magnitude. You're right, and a positive increase. In the context of vectors, the terms magnitude and norm are often used interchangeably. They both refer to the length or size of the vector. So for a vector 2, the magnitude 2 is denoted as 2. The norm of a 2 is also denoted as 2. In essence, the magnitude and the norm are the same thing. So in the case where 2 prime is equal to 0, 1, 2 prime, the inner product of it is equal to 0 times 0 plus 0 times 1 plus 1 times 0 plus 1 times 1, which equals 0 plus 0 plus 0 plus 1, which equals 1. And therefore, 0, 1 divided by 1 is equal to 0, 1. Or in other words, 2 prime is equal to 2 prime. So why is it that 2 prime is equal to 2? Let's see what this says. The notation and explanation can indeed be a bit confusing. The process you're describing is part of the Gram-Schmidt orthogonalization procedure. Here's how to understand it. When you're trying to form an orthonormal basis, you want each vector in that basis to have two key properties. Orthogonality, each vector in the basis should be orthogonal, perpendicular to every other vector in the basis. Normalization, each vector in the basis should be of unit length or normalized. Given your starting vectors, the process involves taking the first vector, let's call it I, and normalizing it to create 1. Constructing a second vector that's orthogonal to 1 by subtracting from 2 its projection onto 1, normalizing 2 prime to get 2. If after the orthogonalization process 2 prime already has a norm of 1, like in your example where 2 equals 0, 1, then 2 is already normalized, and 2 is effectively the same as 2. However, in many cases 2 will not have a norm of 1 right after orthogonalization, and it will need to be divided by its norm to create 2, which has a unit length. In your specific example, the step of normalization didn't change the vector because it's already had a norm of 1. I see. So if I did, yeah, let's make this small and let's try it with a different number. 1 second. I'm going high, bear with me. Okay, so let's make this a little bit smaller. Oh man, it's not working. Let me try quit this. Start again. Hopefully it'll work this time. Yeah, just another bug. Okay, right, so if we take the following, where 2 prime is equal to 0, 2, well, let's see what happens, right? So I was going to ask you if that's an acceptable thing, but let's just find out. It's good practice anyway. So the magnitude of 2 will be equal to the square root of the inner product of 2 prime, which in turn, let's do 2 prime is equal to. it'll be 0 times 0 plus 0 times 2 plus 2 times 0 plus 2 times 2. So basically, it's going to equal 4, I guess. 0 plus 0 plus 0 plus 4 equals 4. And then if we now go 2 prime divided by 4, we're going to have 0 divided by 4, and then 2 divided by 4, which will equal 0. 2 divided by 4, what is that? That's 0.5, right? Yeah, it's going to be 0.5. So in this case, that can't be how you divide things. Divide vectors by a number. Identify the original vector's magnitude and angle, depending vector by scalar. Identify the original vector's magnitude and angle, or the vector's component magnitudes. Who are they writing this for? Identify the original vector's magnitude and angle. Angle to what? Terrible. What is vector division? As already mentioned in the comments, you have two ways of multiplying vectors. You have the dot product and cross product. However, the dot product isn't a product. When you multiply two rational numbers, you get a rational number. When you multiply two matrices, you get a matrix. When you multiply two complex numbers, you get a complex number. So you would want your product to satisfy that the multiplication of two vectors gives a new vector. However, the dot product of two vectors gives a scalar, a number, and not a vector. But you do have the cross product. The cross product of two. Now about division. If you have two real numbers, x and y, does not equal 0, we say that x divided by y equals z. Exactly when x equals y, z. So in that sense, you could define a type of division of vectors. However, again, there are some problems with vectors. When we divide by a real number, we can also consider this as multiplying the inverse of y. That is y negative 1. The inverse of y is that unique number y negative 1 such that y negative 1 equals 1. The number 1 is that special number that satisfies that 1x equals x for all real numbers x. And you see that any... How do you do it? Just tell me. With vectors, you don't have such a unit. There is no vector 1, such as the cross product of... So that is why we don't really have a division of vectors that works just like division of real numbers do. So it says here, taking the first vector, let's call it I, and normalizing it to create 1. Constructing a second vector that's orthogonal to 1 by subtracting 2 is... We now divide 2 by its norm. This step involves normalizing the vector 2. To normalize a vector means to adjust its length or magnitude to be equal to 1 while preserving its direction. This is achieved by dividing each component of the vector by the vector's overall magnitude. So let's, I'm a bit confused to be honest, but so if I instead did 2 equals 0, 2, 2 prime would equal square root of 2 prime 2 prime. Therefore, 2 prime inner product of 2 prime will be equal to 0 times 0 plus 0 times 2 plus 2 times 0 plus 2 times 2, which is equal to 4. Therefore, 2 prime, or 2, equals 2 prime divided by 4, which is 2 equals 0 divided by 4, 2 divided by 4, which equals to 0, 0.5. So the Kindle book was saying, we now divide 2 by its norm to get 2, which will be orthogonal to the first and normalized to unity. Does this agree with the premise? We now divide 2 prime by its norm to get 2, which will be orthogonal to the first and normalized to unity. Let's see what this says. You're on the right track, but there's a small mistake in your process. Firstly, when we talk about dividing a vector by its norm, we're actually dividing each component of the vector by the norm. From your calculation, the norm of 2, or its magnitude, is the square root of 4. Oh yeah. Yeah. Silly me. So let's do that instead. Oh, whiteboard's crashed again. Bear with me. Come on. Okay, we're back. So the square root of 4 that didn't work. So 4 square root equals 2. So so this does normalize it. Okay, so then it's going to be 0, 1. Okay, I see. I see. Okay. Right. Interesting. Good. Okay. Thanks for catching me missing out square root. So given that, we now understand at least what it says, right? Which will be orthogonal to the first and normalized to unity. So it's normalized to unity, but will it be orthogonal to the first? I suppose it depends. I guess it means, is it orthogonal to... So if I want to know if 0, 1 is orthogonal 2 is orthogonal to 1, would I imagine 1 as naught? Would I do an inner product between of 1, 2? If it's 0, then it's orthogonal. I can't spell today. I think that's right. Exactly. Okay. So let's do that. Let's go 1, 2 is equal to 0, 1 uh, 1, 0. Ah, no. Um, that's wrong. Sorry. 1, 0, 0, 1. So that's going to be equal to 1 plus 1 plus 0 plus 0, which equals 2. So that is not orthogonal. Sorry, it says which will be orthogonal to the first and normalized to unity. Let me just double check I've done this right. Exactly, to determine if the two vectors are orthogonal, you compute their inner product. If the inner product of the two is 0, then the vectors are orthogonal to them. Given a, b, and 2, the inner product is a times 0 plus b times 1 equals b. So for 2, the value of b must be 0. The value of b is 0, so I've done a mistake again. So I did 1 times 0, which is 0. That's where I went wrong. 0 plus 1 plus 0 plus 0. So that's going to be 1. Wait, let me do this properly. Oh, goodness me, I'm so bad at maths. 1 times 0 plus 1 times 1 plus 0 times 0 plus 0 times 1 equals 1 plus 1 plus, 0 plus 1 plus 0 plus 0 equals 1. So they're not orthogonal to each other. If I plug in 1 as equals 1, 0, then 1, 2 equals 1, 0, equals 1 times 0 plus 1 times 1 plus 0 times 0 plus 0 times 1, which equals 0 plus 1 plus 0 plus 0, which equals 1. Therefore, 1 is not orthogonal to 2. Which is 2, which is the norm of 2 prime. Correct. Based on your calculations, 1 and 2 are not orthogonal since the inner product is not 0. However, there seems to be confusion in your statement. The norm of a vector and its orthogonality to another vector are two different concepts. The norm or magnitude of a vector 2 doesn't dictate whether 2 is orthogonal to another vector 1. It's the inner product that gives us that information. Given your vectors, yeah, but 1 times 0. Oh, I've done this wrong. This is why, because I've done it wrong. It's 1 times 0 plus 0 times 1. Of course it is. Yeah. So I've done it wrong. And so this is also wrong up here. It's not that. It's 0 times 0 times 0 plus 2 times 2, which just ends up being 4. Oh dear, James. Alright, okay. Okay. Which equals 0. I see it's orthogonal. Your previous calculation was incorrect. The correct inner product is 0, not 1. Ah, so they are orthogonal. No, I don't need to put that. So we get it, right? So that's good. We've figured something out here. That indeed, we now divide 2 by its norm to get 2, which will be orthogonal to the first and normalize to unity. So I wonder why that is though. So let's just try and imagine this a bit. It's all well and good learning these things, but until we just need to know the intuition behind it as well. So if we have, let's take this again. So we've got 0, 2 is 2 prime, right? So let's mark this on a little diagram. I think it's to go 1, 2, 3, 4. 1, 2, 3, 4. Okay. And then this one is, let's do this as red. 0, 2. Here we go. Good. Do this again. Okay. And then we found out that 1, no, not 1 prime, but 1 is equal to 1, 0. We'll do this green. So it's sorry, that's not right. I can't even plot bloody things anymore. Jesus Christ. 0, 2. Here we go. And then this one will be 1, 0. Okay. And so then it says that so 2 is equal to 0, 1. Let's make this blue. And that's because we've just scaled it. This one is scaled to a norm, but it's pointing in the same direction, right? So if I do this, and then this, and then this, and then it says, let's go back over here. It says the inner product of them so 2 equals the norm. So when we do the inner product, why are they 0? Because they are indeed orthogonal to each other. Because, okay, but so I wonder if this works. I wonder if this works with different values, right? Though we have to go through the challenge of creating a basis. I feel like I want to do it anyway. I think that's actually part of this question here. So let's continue on. It says finally consider 3 is equal to 3 minus the first basis scaled by the inner product of the first basis and 3 minus the scaling of 2 multiplied by the inner product of III, which is orthogonal to both 1 and 2. Dividing by its norm, we get 3. Third member of the orthogonal basis. There is nothing new with the generations of the rest of the basis. Where did we use the linear independence of the orthogonal basis? Isn't it funny that geometrically speaking that these things, I guess they lose the meaning of geometry because you can't have, so there is nothing, which is orthogonal to both 1 and 2. You can't have something orthogonal to both 1 and 2, right? Because if it was orthogonal, let's try this. If I go with a blue, no, if I go with a purple, if I was to try and do something orthogonal to 1, then it would either be this, this, and then if I wanted to do this, it would have to be this or this. So the idea of orthogonality with a vector space is very, very strange. It doesn't have a geometric representation. Yeah, very strange. Okay, and then it's so we got this. So where did we use the linear independence of the original basis? Ah, well, I think I did this. We used the linear independence of the original basis. Where did we use the linear independence of the original basis? What does linear independence even mean though? Like, what does when it says where did we use the linear independence of the original basis? What does linear independence? Oh, linear independent. Okay, so it's the fact that um you can't you can't use any of the other vectors to make up another vector in the space. So does linear independence mean when you have a vector space whereby none of the vectors can be rotate can be used together in combination to create another vector in that space? You're on the right track. In the context of vector space, linear independences of a set of vectors means that no vector in the set can be expressed as a linear combination of the other vectors in that set. More formally, yeah, if you have a set of vectors, they are linearly independent if the only solution to the equation is equal to 0. Is when all the coefficients Ci are 0. This means you cannot express any one vector as a linear combination of the others. In terms of bases, a basis for a vector space is a set of linearly independent vectors that spans the space. Span means that any vector in the space can be written as a linear combination of the basis vectors. In terms of bases, a basis for a vector space is a set of linearly independent vectors that spans the space. Span means that any vector in the space can be written as a linear combination of the basis vectors. Oh, that feels like it contradicts itself. In terms of basis, a basis for a vector space is a set of linearly I'll say that again. In terms of bases, A basis for a vector space is a set of linearly independent vectors. Basis for a vector space is a set of linearly independent vectors that spans the space. Basis for a vector space is linear independent vectors that spans the space. Any vector in the space can be written as a linear combination of the basis vectors. So when your text asks where did you use linear independence of the original basis, it's pointing to the importance of the vectors in the basis not being redundant or expressible in terms of the others. This property is crucial in various calculations of theorems in linear algebra, including when constructing. I've missed the plot. I've missed it. So let me just go and I think I've asked this before, you see. So was it when we used the 1 minus 1 2 to create a new vector 2? The concept of independence is crucial in the process. I think I need some help here. So I'm a bit confused. You're saying a basis is a set of vectors, or a basis is a vector in a basis is a vector in a vector space that, when combined with another vector in the space, cannot be equal. Let's just ask you, what is a basis again? It's a set of linear independent vectors that spans the space. A basis is a set, like a collection or a bucket of a set of vectors in a vector space that, when combined with each other, cannot be make another of those bases in the set. A basis for a vector space is a set of vectors that satisfies two conditions. A basis for a vector space is a set of vectors. Linear independence. The vectors in the basis are linearly independent, meaning no vector in the set can be expressed as a linear combination of the other vectors in the set. In simpler terms, you cannot build one of these vectors by adding or scaling the other vectors in the set. So we know what linear independence is. I just guessed that, but I didn't realize that basis is a vector space. So is vector space the same as saying linearly is basis? Because or is it that there are more rules to a vector space than just a basis? So let's read this still. Spanning. The vectors in the basis span the entire vector space, meaning any vector in the space can be expressed as a linear combination of the basis vectors. Let me read that again. The vectors in the basis span the entire vector space, meaning any vector in the space can be expressed as a linear combination of the basis vectors. In simpler terms, using the vectors in the basis, by scaling and adding them together in various ways, you can reach any point in the vector space. To illustrate, suppose we consider the vector space R squared, which is the plane of all two-dimensional vectors. One possible basis for this space is 1, 0, 0, 1. These vectors are linearly independent. You cannot build the vector 1, 0 using the vector 0, 1, and vice versa. They span that plane. Any vector in that plane can be created by scaling and adding these two vectors. So a vector space can have bases in it. Yes. And a vector space can have other vectors in it that are not bases. And so if I were to think about this as an object, as a tensor in programming, it might look like this. Lowercase is a basis, uppercase is a vector. And you're saying that the significance of the vector space having vectors and basis is that any of the vectors can be created using the bases, but none of the vectors can be used, any of the vectors can be created, can be combined, can be created using a linear combination of bases, but none of the vectors can be created. Is that any of the vectors can be created using a linear, but none of the bases can be created through linear combination of the vectors. Almost. Let's clarify a few points. A vector space itself contains an infinite number of vectors. Think of R2, the plane of all 2D vectors. It contains every possible 2D vector. In this space, there are infinitely many vectors and infinitely many possible bases. A basis of a vector space is just a specific set of vectors from that space with two special properties. A, they span the entire space, meaning every vector in the space can be expressed as a linear combination of the basis vectors, and B, they are linearly independent, so no basis vector is a linear combination of the other basis vectors. If you have a vector, if you have a vector space, say V, and a basis for V, say ABC, then every vector D in V can be expressed as a linear combination of A, B, and C, but A, B, and C themselves cannot be expressed as linear combinations of any other vectors in V. Other than trivial combinations using themselves. In your programming analogy, think of the entire list ABCD as vectors in the vector space. The subset ABC could be a basis if every vector in the list can be expressed as a linear combination of A, B, and C. And if A, B, and C are linearly independent, D, E, and F are just other vectors in the space. The vectors D, E, F can be represented using A, B, and C, but A, B, and C cannot be represented by linear combinations of D, E, F, unless you use themselves in that combination. The crux is, a basis gives us a coordinate system to express any vector in that space, and no vector in the basis can be made from others in the basis. So it's like a tooling to. I start to see now. I see. So a basis is a separate entity. It's a mapping tool in a way. You have this toolbox of vectors that are called basis because when you combine the tools together, like a pineapple and a banana, you get a smoothie. The smoothie is a vector um, on uh, on a whiteboard. You use okay, so let me just reword this. So basically this is a separate entity. It's a mapping tool in a way. You have this toolbox of vectors that are called basis because when you combine the tools together, um, you get a mapping. That mapping can be used to form a vector on the whiteboard. The whiteboard has vectors all over it. The toolbox has bases all in it, and a combination of the toolbox vectors can make any vector on the whiteboard, the vector space whiteboard. Does the vector space, therefore, does the vector space, therefore, is the vector space a name to encompass both the toolbox and the whiteboard? And the vectors, yeah. Let's see that. It will say almost. You've almost got it. Your analogy is pretty insightful and you're close. Let's refine it a bit. The vector space, whiteboard. The entire whiteboard represents the vector space. It has an infinite number of vectors drawn in it, representing every possible vector in that space. Basis, toolbox. The toolbox contains a set of special tools, each one representing a basis vector. These are not the only tools you can have, but they are a unique set because they have two key properties. They can be combined to draw any vector on the whiteboard, and no single tool in the box can be replicated using the other tools. When you want to draw mapping combination drawing, when you want to draw a particular vector on the whiteboard, say vector D, you use the tools in the toolbox in a specific way. You might take a bit of tool A, a bit of tool B, etc., and combine them to get D. This combination process represents the linear combination of basis vectors to get to any other vector in the space. Entire scene, vector space plus basis. The whole scene, including the whiteboard and the toolbox, represents the vector space, along with a specific basis chosen for it. The vector space itself doesn't change, but you can choose different toolboxes basis for it. So in summary, the whiteboard is the vector space. The toolbox is a basis for the vector space. Particular basis for the vector space. The entire scene is a vector space with a chosen basis. Note that there are many possible toolboxes, bases, you can choose for the same whiteboard. Ah, that is a legitimate win there, I think. Legitimate win. That's lovely, and to imagine these things. I think what I'd gotten confused about was I believed that the vector space itself was, well, I correctly determined that the vector space was the basis and the vectors, but they are still separate things. They're not like an array with all these vectors in. And I don't think the book made it very clear, but nonetheless, I don't think this is the best read. Actually, I was looking through YouTube, and this is not one of the books anyone recommended um, for like someone coming in from quite a newbie background. Good, okay. So it says, where did we use the linear independence of the original basis? Well, we used it because the fact that let I be a linear independent basis. The first vector of the orthonormal basis will be. Let's also clarify this. Thanks. That's awesome. When it comes to linearly independent basis and orthonormal basis, are we referring to the separate toolboxes? Like, here's the blue toolbox, and here's the red toolbox. Is there any interesting um, analogy for why they are mentioned at the beginning of the page in this way? Let I be a linearly independent basis. The first vector of the orthonormal basis will be. It's just quite difficult to separate myself from the or difficult to draw insight from the highly technical wording used in mathematics. Different types of bases can be likened to different types of toolboxes, each with its unique characteristic or advantages. Let's extend the analogy. Linearly independent basis, the basic toolbox. This toolbox contains vectors that are not redundant. No tool in the box can be made by combining the others. This is what we may mean by linearly independent. However, the tools might not be the most ergonomic or intuitive to use because they might not be at right angles to each other, orthogonal, and may not have a unit length normalized. For instance, in a 2D vector space, a whiteboard, think of this toolbox as having a ruler and a protractor. Whoa. They can, well done, GPT. They can help you draw any point on the board by measuring length and angle, but they might not be the most intuitive tools for the job. Orthonormal basis, the premium ergonomic toolbox. GPT-4, bloody hell. This toolbox is an upgrade. Every tool inside it is specially designed to be at right angles to every other orthogonal and is of unit length normalized. This makes them incredibly intuitive and straightforward to use. In the 2D analogy, think of the toolbox as having a grid overlay for the whiteboard. If you want to draw a point, you just count squares in the x and y directions. It's more intuitive than the ruler and protractor because the basis vectors are orthogonal and of a consistent normalized length. Why start with one and move to the other? Mathematically, it's often easier to start with any given set of linearly independent vectors, the basic toolbox. However, for many applications, it's convenient to work with orthonormal vectors, the ergonomic toolbox. So the process you're seeing is a kind of toolbox upgrade. You start with a basic set and refine it to get the premium ergonomic version. In essence, linearly independent basis. This was fucking brilliant. Well done, GPT-4 team. Be proud. Be very, very proud. This was freaking brilliant. Freaking. Let's do freaking. Um, in essence, a necessary condition for any basis. In essence, linearly independent basis. A necessary condition for any basis. No vector in the basis can be written as a combination of the others. Orthonormal basis. A luxury or ergonomic version of a basis, where vectors are not only linearly independent but also perpendicular to each other and of unit length. This makes calculations easier and more intuitive in many scenarios. Oh, if that's right, I mean, it can make up stuff, right? But if it's right, oh man, is that not the most incredible? Like, I don't even care if it's wrong. Um, okay, let's imagine it's right, because I'm grinning here, right? Let's see how useful it is now, because I think it's not. Perhaps I didn't get too much from it, apart from the fact that I've clarified in my head where to put things, right? So it says let one and I and 2i. Let's call them. I just hate the I. I'll call it E. Let I and E be a linearly independent basis. So we've got this we've got this toolbox and we've got two vectors in it, and they can be added together to make other ones, um, but no none of the other two. If there were more than just two, we couldn't make a third one from it. Um, we couldn't make the third one that might be in the box. So let's imagine there's only two. The first vector of the orthonormal basis will be, so now we want an upgrade of these tools. So it says the upgrade is equal to the vector itself, the tool in the box, divided by the length of that tool, where the length of that tool is equal to the square root of the inner product of them. Okay, we'll say tool is vector now. We've got it. And note that in here we do not get to use the other box, right? We're just saying that this operation will give us a new ergonomic tool. And it says clearly, if you take these old tools, they equal 1, and so the inner product is equal to 1. As for the second vector in the basis, consider this. So now we're still at the orthonormal basis. Second vector in the orthonormal basis. Consider you take the 2 and you can minus using our new tool and take an inner product to get the second one. Aha! Which is 2. Which is II, minus the part pointing along the first unit vector. Think of the arrow example as you read on. Not surprisingly, it is orthogonal to the latter. So now we've got these two new special tools are equal to the first ergonomic tool that we made. Aha, so it says not surprisingly, but I'm just not there yet, right? So that's fine. I'll take the hit on that one. Like pew, pew. And it says we now divide 2 prime, which is this other special tool that we had, to get yet another tool, but the okay, no, so it's just saying that we've got this tool, but we need we now divide 2 by its norm to get, which will be orthogonal to the first and normalized to unity finally consider 3. Alright, I think our toolbox could be used quite nicely here for all of these. I think I might think about that when I'm getting into bed and stuff, because that's very interesting. There's a lot of juicy information here. And so then it asks, where did we use the linear independence of the original basis? Well, we used the linear independence of the original basis when we linear independence of the original basis to get our new tool, basically. So it it asks where um, where did we use the linear independence of the original basis? Well, we used it to get our new ergonomic um, one ergonomic tool called one, right? Um, it it just it just so happens that the vector divided by the magnitude of itself allows us um, to create our new ergonomic orthonormal basis, which is more helpful. Um, However, so what's the intuition here though? So okay, we've got those things and they're tools and we can put them together and stuff like that. But why is that the case? Well, it's because of the nature of the fact that you can divide it by the normal, where the normal is equal to the square root. Um, however, it's more. However, am I right in saying that the detail of why it's so significant is that when you take an independent um, vector, then a, a, a independent basis, and you do the math on it, divide by its norm, um, it makes an orthonormal basis because why does it make an orthonormal basis? Okay, let's try and draw this then, because I'd quite like to see this now. So we've got our let's say I is equal to 1, 2, and I. Oh no, hang on. These can be, so I can be equal to 0, 2. Actually, let's just do 2, 2, 0, and this could be 0, 2. Now it's saying that so what's the length of, so the length of it is equal to the square root of the inner product of 2. So let me just go back, hang on a second. Inner product of 2 uh, 2, 0. I haven't done that yet. Alright. Fair enough, I'll just do it now. So the inner product, just get rid of this a sec, of 2 with 2 is equal to 0 times 0 plus 1 times 1, which equals 1. I didn't want that, I wanted that's what I meant to do. Which is 2 times 2 plus 2, 0, and then 0, 0, 2 times 2 is 4, and then 0 times 0 is 0. Yeah, so it's going to be equal to 4. And then it's the square root of 4 equals, what we got here again, equals the magnitude. Okay, so the magnitude is square root of 4, which equals to 2. So if we have 1, 2, 3, 4, 1, 2, 3, 4, and we plotted I as 2, 0, 2, 0, do that here, and then we're going to divide that by 2, we're going to get that. Let's now try this with different numbers. If I did this with 6, right? Let's do that now. 6, 0, 0, 6. Okay, it doesn't matter really. Then it's going to be 6 times 6 plus 0 times 0, which is 36. And then the square root is always going to be, I see, okay. So square root of 36, what is that? 6, I guess. Just make sure. 36, 6. So in this case, this is purple. Let's do this green. We're going to go 6, 0, 4, 5, 6. It's over here somewhere. And then we're going to scale it by 6. So it becomes 1. So we always get the orthonormal. So however, I'm right in saying that the detail of why it's so significant is that when you take it into basis and you do the math on it, divide it, it makes an orthonormal basis because it will always end up with a normal of a normal because it has been scaled by itself. The square root of the original inputs, something like that. I just can't bother to type properly. Maybe it will just help me out anyway. Yes, you're on the right track. The importance of linear independence in this context is primarily to ensure that the starting set of vectors, the original basis, has meaningful, non-redundant information. Without linear independence, one or more vectors in the basis wouldn't contribute anything new. They'd just be combinations of the others. The process of taking a linear independent set and transforming it into an orthonormal basis involves two primary steps: making the vectors orthogonal, normalizing the vectors. So linear independence of the original basis ensures that we're not wasting our time on redundant vectors. The process of Gram-Schmidt orthogonalization, which is effectively what you're doing when converting a linear independent set to a normal orthonormal set, then takes this basis and makes it orthogonal and normalized. The significance of the orthonormal basis is manifold. Computational simplicity, inner products between orthonormal. Okay, so that's what that was. And then it says, what if we had started with a linearly dependent basis? Well, in that case we wouldn't end up with orthogonal um we wouldn't end up with orthonormal bases. So we wouldn't. So let's think about one that's can you give me an example with really small whole numbers of a linearly dependent basis, please? I see. So linearly dependent means we we can create uh, a tool in the basic box with two other tools. Therefore, what's the point in having that tool? It just weighs us down when we carry the toolbox. And although we can be happy with the other ergonomic ones that we can use that we created from the original from the basic toolbox, will always be weighed down by that linearly dependent one in the basic toolbox. Exactly. Your analogy captures the essence of it quite well. When we talk about a set of vectors being linearly independent, we're essentially saying that there's redundancy in the set. At least one of the vectors doesn't contribute any new direction or information in the set. In terms of your toolbox scenario, why carry on an extra redundant tool when it doesn't provide any unique function or value? For many mathematical and practical applications, working with linearly independent set of vectors is more efficient and useful. Lovely jubbly. Every vector in the set has its unique direction, ensuring that they span the space without any excess baggage. So when you're constructing or working with the basis for when it says what if we had started with a linearly dependent basis, we would end up not being we would end up with if we start off with a linear dependent basis, then is the detailed answer that we just simply couldn't create an ergonomic tool, an orthonormal basis, or is it that we'd still possibly be able to create a basis because it would never um, but because it would never be able to be orthogonal to the orthogonal. Let's just can you pad this out a bit? I'm losing the will to live. Absolutely. Let's break that down step by step. Orthogonal vectors. Two vectors are orthogonal to each other if their inner product is 0. This means they are at right angle to each other in a geometric sense. Orthonormal basis. This is a set of vectors that are not only orthogonal to each other but also of unit length. Linear dependent basis. In this scenario, one or more of the vectors in the basis can be written as a linear combination of the others. This means there's redundancy in the set. Now, if you try to create an orthonormal basis from a linear dependent set, problem with orthogonality. When you attempt to orthogonalize vectors that are linearly dependent, using the Gram-Schmidt process, for example, one of them will become the zero vector. This happens because during the orthogonalization process, when you project one vector onto another that's essentially a scaled version of itself, you end up subtracting the whole vector away, leading to a zero vector. Ah! Bing, bing, bing! Zero vector issue. A zero vector cannot be normalized, dividing by its magnitude. Sorry. Zero vector issue. A zero vector cannot be normalized, dividing by its magnitude, which is 0, is undefined. So achieving normal in orthonormal becomes impossible. Wow! Loss of dimensionality. Even if you disregard the normalization issue, having a zero vector in your basis reduces the effective dimensionality of your space. In other words, you lose the ability to represent all vectors in your space using that basis. Yes, okay, I see this. In conclusion, starting with a linearly dependent basis is problematic because it hinders the creation of a normal orthonormal basis. The process either collapses one vector to 0, making normalization impossible, or reduces the representational power of the basis. This isn't just a theoretical concern. In applications like quantum mechanics, for example, having an orthonormal basis is crucial for probability calculations and the general formulation of the theory. Booyaka. Yes. Amazing. Amazing. Okay. I'm so happy. Good. Good, good, good. It says, then at some point, a vector like 2 or 3 would have vanished. It would have become 0, like it said, putting a stop to the whole procedure. On the other hand, linear independence will assure us that such a thing will never happen, since it amounts to having a non-trivial linear combination of linearly independent vectors that adds up to the null vector. Go back to equation for 2, 3, and satisfy yourself that these are linear combinations of the old basis vector. So we finally get to the exercise. I'm so glad I went through that again because I'd done it on the weekend and I felt like generally quite happy with myself. And now with this toolbox thing, um, and the understanding of why whether it becomes 0 and then it can't be orthogonal, and even if you could, then it would be um, more dimensions to your space. Wonderful. So it says, and I think I'm too tired now to do this, but I might chug on tomorrow though because this is quite exciting. Exercise 1.3.1. Form an orthogonal basis in 2 dimensions, starting with. So let me just note that I did try this. So I've got my little equation up here. I did go through this, but I think what would be nice is to have to recall this tomorrow. So I will at least do this again even if I do it now. But let's go to a new page and let's start this. I'm so excited. I'm looking forward to a nice beer after this as well. Alright. Quantum physics, baby. Mathematics. Oh yeah. So it says create an orthogonal basis. This is the ergonomic baby. An orthogonal basis, not orthonormal. In 2 dimensions, starting with A equals 3i plus 4j and B equals 2i minus 6j. All of them are vectors. Can you generate? I see. Yeah, and then it says about orthonormal. So form an orthogonal basis in 2 dimensions, starting with this orthogonal. Oh, okay, so this is really testing it now, isn't it? let's see, orthogonal. So if you've got two vectors and they're that, then to make it orthogonal, so that makes it orthonormal, but to make it orthogonal, orthogonal, we would take the B equals, oh, well, form an orthogonal basis in two dimensions. Let's say C then. Let me just track this out. C equals B minus, and then so we need the orthonormal to do this. So it says, can you generate another orthonormal basis starting with these two vectors? Form an orthogonal basis. So is this just saying just take the orthogonal means, well, let's see if it's orthogonal, right? So let's do AB equals, let's just see how it goes. So it's going to be, it's 3i plus 4j plus, it's a plus b, isn't it? It's a plus b. So it'll be 3i plus 2i is 5i, and then it's plus 4j minus 6, 4j plus minus 6j is minus 10j. So I think because this is not 0, it's not orthogonal. So how do we know what the bases are? Because these are not, so form an orthogonal basis in two dimensions starting with, maybe I need some help here, because I don't think I know enough about this stuff to collect to collate the two. So when it says, so let's see, exercise 1.1.1.3.1. Okay, so I haven't talked about this one yet. When it says on exercise 1.3.1, form an orthogonal basis in two dimensions starting with, so they are vectors. I totally forgot they're vectors. Bear with me. Haha, bear with me. This is the problem with not putting these on, right? Don't be James. Do not be James. Let's do this again. Yeah, so it's the inner dot product. Well, I guess I could plug numbers in, but let me think about this. Let me think. Vector A is equal to 3i plus 4j. Vector B is equal to 2i minus 6j. Are we saying here that the the scaling of these and being able to plus them together, equaling a new vector, makes them a basis? So I and j are a basis. If I and j are a basis, then we can state that a second basis would be it would be C would be equal to Um, B, no, no, yes, no, exactly. Uh, these these are already making a basis, so A is the basis. A is the basis of 3i and 4j. So it's actually, ah man, it's I. If I were to do, no, because so these are plussing. So because they're plussing, it could be the inner product. The inner product would be, no, no, no. But it's saying that the combination of the two vectors equals the vector. So these are basis vectors. They're linearly or form an alphabet in two dimensions starting with. They might be linearly independent. We don't know. Um, well they must, yeah, sorry, they are linearly independent because they can make A. Well they might be linearly independent because they can make A. Okay. And so if that's the case, then we kind of have this 1 equals 3i plus 4j divided by the magnitude of 3i plus 4j. Um, in fact, it would be, so that's what I was saying. So the one in this equation over here, this one over here is the A. So 1 is equal to A. And so to create a second one, we could do B, so 2 prime is equal to 2i minus 6j divided by 2i minus 6j, which is equal to B. Well, I don't need these things, but anyway. Oh, I need that. That was something I need. This you do not. Right. And if that's the case, then the third one will equal or 2, 3 prime is equal to a third vector. We could do anything, couldn't we? We could do C. Oh, C equals, I know, 2i plus 2j j. Um, and so 3 would be it would be 2i plus 2j divided by that equals c. But it says form an orthogonal basis in 2 dimensions. So it means that these together must be 0. So if I were to go and figure out if these are orthonormal, well, I guess I and j just need to be, let's see, if we did I hat equals 1 0 and j hat equals 0 1, we end up with 0 0 1, and so then we're going to do, oh fuck, let me just do it again. I can't remember where I did it now. It would be 3, so 3i is equal to 3 times 1 and 0. Let's actually put that, yeah, 3 times 1 and 0 time and 3 times 0, which equals 3 0. And then 4j would be equal to 4 times 0, 4 times 1 is equal to 0 4. And so 3i plus 4j is equal to 3 plus 0 and then 4 plus 0, which is equal to 3 4. And then if we then want to find out if that is orthogonal to B. So let's do that now. 2i is equal to yeah, 2 1. Well, yeah, okay, let's just do it. No, what's no point. It's just going to be 2 0 and then 6j will be equal to 0 6, and then 2i plus 6j will be equal to 2 6. And then now we want to take the inner product of the two. So the inner product of A and B is equal to 3 times 2 plus 6 times 4. 6 times 4. Sorry, 6 times 4. I'm sorry. 6, 12, 18, 24. Let me just do that because I'm just so terrible at mental math. 6 plus 6 times 4, 24. Yeah, that'll do. I did say cube 6, but anyway. Okay. And then, which equals 30. So the inner product is 30. So the inner product cannot be so A and B are not orthogonal to each other if I put them in as 1, 0, and 0, 1. So I'm a bit confused. Let's get some help from it. So when it says so form an orthogonal base in 2 dimensions um, starting with A and assume all letters are vectors with hats on them. A equals 3i plus 4j. B equals 2i minus 6j. I tried substituting sub sub substituting yep. I equals 1 0 and j equals 0 1. But after calculating, I found out that 3i equals 3 times 1, 3 times 0 equals 3 times 0. Sorry, 3 0. 4j equals 4 times 0, 4 times 1 equals 0, 4. 3 plus 3i plus 4j equals 3 plus 0, 4 plus 0, 3, 4. I did the same for 2i plus 6j. 2i equals 2, 0. 6j equals 0. 6j equals 0, 6. After calculating, I got, and then 2i plus 6j equals 2, 6. And then I took the dot product A and B, which equals 3 times 2 plus 6 times 4, which equals 6 plus 24, which equals 30. So these are not orthogonal. So how do I go about performing this exercise? seems you correctly express the vectors A and B in terms of their components. Your computations are correct until the dot product, where there seems to be a mistake. 3 times 2. 3 times 2, 6 times plus 6 times 4. Dot product is 3 times 2 plus 4 times negative 6 equals 6 minus 24 equals negative 18. Okay, cool. Given that it's not 0, the vectors A and B, let me just correct that. 6 times negative 4. Yeah, 4 times negative 6, I see. 4 times negative 6. Because this is all negative. It's not plus, it's minus. Anyway, yeah, and so to create an orthogonal basis using A as the starting vector, start by normalizing A to make it a unit vector. Okay, so let's do that. Let's do that. So let me just copy A over. Delete that, delete that, delete that, and get that. So we'll normalize it. And so that is going to be, it's the dot product of A is going to equal, and they've plugged in what, like, yeah, the things I put in. So let me just get those as well. That's copy, paste that over there. Oh, she's a little far off. One sec. Okay. So the dot product of that is going to be, oh, we've already done that as well. How annoying. Yeah, it's going to be this. Let's just take the whole thing. And then we'll delete a bit. So it's going to be 3 times, one sec. One second. Just need to zoom out a little bit. 3 times 3 plus 4 times 4, which is 9 plus 16. 9 plus 16. 9 plus 16 is 25. So, given that let's see this, A, the product of, it says, start by normalizing A, and I want to normalize A. Oh, normalizing A. And to normalize A, what did we do? To normalize A, we took the square root of the inner product. We took the square root of the inner product. So the normal of A is equal to the square root of 25, which is equal to 5. Okay. We align so far. And then it says, so a prime is equal to 1/5 of 3, 4. Because a prime is oh, a prime. Ah, a prime is where a is the magnitude of a. To get to the prime, oh, I can't remember this now. We now divide 2 by its norm to get 2, which will be orthogonal to the first and normalized to unity. So now we get a prime is equal to a over a, which is equal to 3, 4 divided by 5, which is equal to 3 divided by 5, which is equal to 3 divided by 5, 4 divided by 5. What does it say here though? It says 1/5 of 3 of 4. 0.6. Let's see if that's correct. Let's see how good GPT-4 is at straight math. 3 divided by 5, 0.6. Yeah, cool. 4 divided by 5, 0.8. Wonderful. 0.6, 0.8. Good so far. Okay, following along. And then it says, so that's a prime. And then it says, now to find an orthogonal vector to a, take the negative reciprocal of the slope. Negative reciprocal of the slope. Considering a and b as points in a 2D plane, the slope of a is 4 over 3. So negative reciprocal is minus 3, 4. Using this slope, an orthogonal vector to a would be, now to find, take the negative reciprocal of the slope. It's just lagging for a bit, but it says when you say take the negative reciprocal reciprocal of the slope, what did you mean by this? Considering a and b as points in a 2D plane. Taking the negative reciprocal of the slope is a geometric way of finding a line that is perpendicular to a given line 2D. When we talk about the slope of a line, it is often referred to as the rise over run. Specifically, if we have a line that goes through points x1, y1 and x2, y2, its slope m is defined as y2 minus y1 over x2 minus x1. Now if we have a line with a slope m, a line perpendicular to it will have a slope that is the negative reciprocal of m. Mathematically, if our original slope is m, then the slope of the line perpendicular to it is 1 over m. So if, for example, if the slope of a line is 2, the slope of a line perpendicular to it is 1 over 2. If the slope of a line is 3 over 4, the slope of a line perpendicular to it is 4 over 3. In the context of your problem, the vector A can be seen as defining a line with a slope of 4 over 3. because of every 3 units in the x direction it moves 4 units in the y direction. So a vector that is orthogonal to A will have a slope of minus 3 over 4, which is the negative reciprocal. This context is very helpful. But in the context of our in the context of our numbers, then the slope would be negative 0. Negative 0.1 over 0.6. And take away, no, divided by, no, take away. So if this is, okay, this is not clear to me. If 0.6, so we've got A prime now, and it says so now to find orthogonal vector to A, take the negative reciprocal of the slope. Considering A and B as points in 2D plane, the slope of A is 4 over 3. Because it's, I see. That's that part, but this is a 3/5, so why is it 4 over 3? Because it's just complete. Okay, in the context of our numbers, you said slope of A is 4 over 3, so the negative is negative 3 over 4. But actually, isn't it, actually what happened to our fake numbers, 0.6, 0.8? Is there a reason you got rid of these? You're right, I did transition away from the normalized version of the vector A and refer back to the original vector when discussing the slope. Let me clarify, the vector 3 did has a slope of 4, 3. When we normalized A, we got the vector 0, 6. Normalized version still points in the same direction as A, and thus has the same slope of 4, 3. The magnitude length of the normalized vector is 1, but its slope or direction remains unchanged. We're discussing orthogonality. The magnitude of the vector isn't the primary concern, it's the direction. So when you're dealing with A or its normalized version, the logic for finding an orthogonal remains the same. To find a vector orthogonal to A, you would look for a vector with a slope that is the negative reciprocal of 4 over 3, which is negative 3 over... M equals B... M equals B plus C. Is it MX? MX equals... I'm totally lost. Sorry, I'm totally lost. You had me up to the point where we worked out that the A prime was A divided by magnitude of A, which ends up being 0.6, 0.8. But then you used a technique that I'm not familiar with. I now understand that the slope is y2 minus y1 over x2 minus x1, but how does this help with a coordinate of 0.6, 0.8? That means the reciprocal would just be 0.6, 0.8, because there's no second coordinate to subtract from, no line. Puzzling confused. Let's break it down step by step. The vector A can be visualized as an arrow pointing from the origin to the point 3, 4. The slope of this vector is the same as the slope of the line that passes through the origin and the point 3, 4. The slope m of any line or vector in the plane is given by m equals rise over run, or for a vector m equals y over x. For the vector A with coordinates 3, 4, the slope is m equals 4, 3. Now, if two vectors are orthogonal, their slopes are negative reciprocals of each other. This means if one vector has a slope m, a vector orthogonal to it will have a slope negative 1 over m. For a vector A with slope 4 over 3, an orthogonal vector will have slope m prime equals negative 3 over 4. To find an actual orthogonal vector, we can use the slope m prime. Any vector that has the slope will be orthogonal to A. Why is it 3, 4? Did you just remove the I and j vectors from the original A equation? How so? In the exercise you provided, the vectors were defined in terms of the standard unit vectors I and j. The unit vectors I and j are represented as 1, 0, 0, 1. When you expand the vector, that's because I did that. When you expand the vector A in terms of these unit vectors, you get 3, 4. Okay. This is the coordinate representation of the vector A in a two-dimensional Cartesian space. Oh, I see. So actually, I think it must have gone on to say something then, because we got to here. Start by normalizing A to make it a unit vector. So it's just saying. Now to find the orthogonal vector to A, take the negative reciprocal of the slope, considering A and B as points in 2D plane. The slope of A is 4 over 3, so the negative is negative 3 over 4. Okay. Using this slope, an orthogonal vector to A would be 4, negative 3. Normalize B to get a unit orthogonal vector. Okay, therefore the orthonormal basis starting with A in 2D is A prime, which is equal to 0.6, 0.8, and B 2 prime, which is equal to 0.8, negative 0.6. Square root of the inner. I think it's okay. It's taken a few steps away from me here, so I've lost the thread. However, let's just stop there because I'm pretty tired. I've been working like all day, like literally from like 9 in the morning. So let's stop there. I'll go have some dinner and stuff like that, and then tomorrow we'll do this question again with a fresh set of neurons firing, and see if I can understand what's just happened there. I think sometimes I simmer away in my sleep anyway, so that was really fun actually session. There was a good point there where everything started clicking with the toolboxes, so this is good progress. Although we're still on the same page for like 3 or 4 sessions now, we're almost there. I don't want to move on until I